Okay, hi everyone. So after a long time, we're back with another episode of Math Talk. I'm here with my friend Dr. Anwesh Ray, who's assistant professor at the Chennai Institute. Mathematical Institute, sorry. Right. Chennai Mathematical Institute, yeah. Yeah. So yeah, thanks for joining me today. Maybe to just kick things off, if you want to say just a couple of words about the sort of research you do and things you normally think about.
Yes, so I work mostly in algebraic number theory, with a little bit of arithmetic geometry as well. So mostly I study questions that involve like the intersection of Galois theory with arithmetic statistics and Iwasawa theory. And yeah, so I have like various research interests, which span from theory of Galois representations, Iwasawa theory, arithmetic statistics, some arithmetic topology as well.
Nice, nice. It's a good breadth
Yeah.
of stuff. Yeah. So you probably know, you mentioned you watched one or two of my previous interviews, so you probably know one of the things I like to start with is going back to the very beginning with people. And I like to ask, where and when did you first discover that you were interested in mathematics? Like, was there any particular people? Did you get started at a young age? Like, were you good at it in school or competitions or something? Like, when did that sort of first click for you that math is something that you're drawn to?
So I think for me, the answer is going to be really boring because it's going to. So I think maybe I can like tell you a story.
Sure, sure.
Get on to the answer. So when I was an undergrad, I was a TA for an algebra number three conference or workshop for some of the sessions, and that's where I met Mishti, who is my current partner. And
So wait, hold on a second. But here you're saying you're already a TA for a math course at this
yeah,
point?
but I'll tell you a story.
Okay.
Yeah. Okay. So right. So she was doing a project which involved like a little bit of Galois theory,
Uh-huh.
and she was just trying to ask me like, when did you first encounter Galois theory? I've not. She was a little bit new to it because she was like a first year.
Mm.
And I think what I said to her was, well, I learned some of that in ninth grade.
Wow.
So I think she eventually went and told a bunch of people that this guy is like, a complete show off. But yeah, I think that was a little bit of exaggeration, but yeah. So I think I sort of got into math like fairly early.
I see. I mean, definitely, if by ninth grade you were doing Galois theory, yeah.
It's a little bit of an exaggeration.
Yeah. Okay.
Not a huge exaggeration, but a little bit of an exaggeration.
I see.
Yeah. So I mean, when I was maybe like I don't know in sixth or seventh grade, I sort of took an interest in learning some advanced mathematics, and that was because like I read some of these like popular science books about like some cool stuff about astrophysics and stuff like this, and I didn't really understand what was going on in some of these books. So I was like, oh yeah, I need to learn like a lot more mathematics in order to understand some of this stuff. And back then I was kind of like, a little bit more open to some of this, so than I am right now. So I started learning like some, basic, high school algebra and some calculus from, some of the 10th, 11th grade and so on. And then I kind of like got a little bit bored with it because, there was these like repetitive exercises with derivatives and integrals and stuff. So I didn't really like I wanted to know what I should do next because it was getting like really repetitive, and I was just like doing this stuff by myself in the library.
Right.
And yeah, not really focusing on the other subjects and not getting very good grades.
Right.
So that's kind of like when I stumbled upon this book. It was a book by Montgomery, Niven, and Zuckerman, which is like
I think I know the one. I have a copy of
yeah,
it.
yeah. So this is like around 8th grade, and that's when I started learning about Fermat's little theorem, divisibility, the Euler-Toscan function, and proofs of quadratic reciprocity and that kind of thing. And that's when I was like, whoa, that's like 1,000 light bulbs like clicked.
Right.
Like, okay, like now I understand like what I really want to be doing and how I want to be spending my time.
Right.
So then, I mean, it took me a while to sort of like understand some more of this stuff because it was like it got really complicated very fast. And so around my 9th grade, that's kind of like when I reached out to some professors who sort of they basically asked me to learn some abstract algebra.
Right. Right.
And yeah, so I picked up some of that stuff, and then I learned a little bit more grad level stuff before I went for my math degree as an undergrad. So yeah. Sorry, that was a long answer.
Yeah, no, I mean the point of these talks is to hear the long answers that
so like I didn't really take much of an interest in math competitions. Really, I was like more into trying to learn some of the some of the things that interested me. Like I wanted to learn a little bit more about algebraic geometry.
Right.
Before I yeah, but it was a little bit hard because I remember looking at the definition of a variety and I was like, and then I saw the definition of a scheme and I was like, okay, this is like way too hard. But yeah, but I had a good idea of like what were the different things in I would say like an advanced undergrad / grad level course, but I didn't really have the background to have actually done things systematically at that point. So
right.
yeah.
So
I'm not going to say that I learned all of that stuff. But I had a good understanding of it. So
yeah. I think the part about reading some of the like physics books and stuff and realizing that you needed more of the mathematical background. That's similar what happened to me as well. I started off by reading, as I got interested in physics, you read some like pop science, pop physics books and it's like, oh, that's great. But then eventually you come to this point where you're like, oh, there's something missing here. And that's
so like I think what I learned very early on, like when I was reading this kind of stuff is in high school was that I was like just more naturally interested in some of the algebraic things as opposed to some of the more analytic things that like and I also like wasn't exactly so it's like I wasn't really fascinated in the real world. I was really not really fascinated in understanding how things worked in the real world. So that wasn't really my focus.
Yeah.
And I tried learning more about physics and more about some of the things that initially interested me as a math to sort of take take down the mathematical path, but I didn't really find that kind of stuff all that.
Yeah.
I found it just difficult to get motivated in that sort of stuff. So
yeah, well, I think I mentioned this to you over dinner the other night. I think it was you. I mentioned this too that I've been thinking about, oh, maybe I should prepare for alternative careers in industry or something. I started looking at math finance, for example. But of course, what are the parts of math finance that I gravitate to and most interested in? Well, it's not the hard applications. It's like, oh, the advanced measure theory, and oh, we're taking a measurable function valued in a Hilbert space. I'm like, oh yeah, like let me read more about that part. Of course, it's not the part that's most important, most hireable. But yeah, it's like I can't help it.
Yeah, but these days I do take a little bit more of an interest in like some of the applied aspects of number theory, simply because it's not because like I'm sort of inherently interested in applying mathematics to the real world, but just simply because the real world does throw up a lot of interesting mathematical problems, which could further enrich my interest in pure mathematical things. So it's like purely from yeah, I mean, a very good.
It's out of a drive to dive deeper into the pure
Yeah.
mathematics. Yeah.
I mean, a very good example of this would be like, okay, like if I,
You can.
yeah, so like if I wanna like, if I wanna understand more combinatorial properties like, partitions or quadratic forms and so on, we can sort of construct these generating series and try and study the properties of these generating series. But then we find out that these are actually related to modular forms, and then okay, then physics tells us something about, the behavior of these functions.
Right.
So it's more like using physics and like the applied stuff, okay, as a tool to sort of to sort of solve pure mathematical problems. So okay.
I mean that's such a surprising thing. I went to summer school for undergrads at the University of Alberta. I was young, and I remember there was a course in enumerative geometry, and there was this, this one formula, for example, that came up that, the physicists predicted this formula should be true at some conference, some formula in enumerative geometry, and initially the mathematicians interaction at this conference, they're like, no, this is impossible. Like this formula it's like too nice or whatever, couldn't possibly be true. And yet, sure enough, it turned out to be correct. But the sort of the reason why they even guessed such a thing that the mathematicians would never have dreamed of is by some physical motivation, and yet it became this theorem in very abstract pure mathematics. So
right.
yeah.
I mean, I think Boschard's proof of the monstrous moonshine conjecture is a very good example of this, I think.
Right.
So it's a conjecture about the representations of the monster group, and it's the relationship between those representations and the coefficients of certain modular forms.
Yeah.
And it turns out that by studying something that comes up, some of the algebras that come infinite dimensional algebras that come up in physics, we can actually actually prove such a. I mean, Bosch has actually proved this conjecture.
Right.
Okay, so I'm not an expert in that area, but I think that's a very good example of how you might not be interested in the real world and how it works,
right.
But then okay, here it gives you something
right.
Mathematically important, at least. Yeah. So
yeah.
But yeah, that has not yet featured in my research so far. But I'm sort of I'm really open to that kind of thing as well.
Nice. And so okay, so it seems like you were bit by the number theory bug at an early age,
right.
And that stayed with you the whole time. So I guess already before you even started your undergrad, you knew that number theory, generally speaking, was something you wanted to do, or how did your taste develop throughout your undergrad, and how did you end up going to where you did your PhD and who you worked with and your research there? Like how do we get to that?
Right. So so the institute where I'm actually a professor right now, that's where I went to as an undergrad.
Oh, okay.
Yeah. And they offer a 3-year undergrad degree.
Right.
And it's basically focused on like I mean we had mostly like it's focused on like pure math majors. They do have some minors in computer science and physics as well. So like when I was an undergrad, I took a lot of these grad level classes and actually, did the problems more systematically this time.
Right.
And I took a lot more interest in like algebraic geometry, like just like and so I was a little bit conflicted about whether I would become a number theorist or whether I'd become an algebraic geometer.
Right.
So then, yeah, I was kind of like interested in both, I would say. And then I did a 3-year undergrad. I did a 2-year master's at this place, and then I went to Cornell.
So what was the topic of your master's thesis? What did you do in your master's?
Oh, I was not required to do a master's.
Oh, okay. So it was just course based.
Yeah.
Okay. I see.
after that, I went to Cornell. I worked. I had a number of options, and I worked with Ravi Ramakrishna.
Oh yeah.
So, and that's around the time when I sort of decided that I would actually sort of try and focus mostly in numbers.
Right.
And
So was that because you were just doing that work under him and you found like that's what you really connected with the most, or was part of it maybe the fact that you put this effort into learning the foundations to work with him and you figured, oh, I'll keep the momentum? Was it maybe a mix or something else?
yeah, so when I went to grad school, I basically spent a lot of time trying to learn a lot about what people were doing at Cornell. Taking a lot of attending a lot of like grad student meetings and also reading papers written by various people.
Mm.
And I took some interest in the geometric Langlands program
Oh,
at the
okay.
beginning. I took some more interest in some combinatorial algebraic geometry as well, and uh, I was also open to like some algebraic topology stuff. But I think eventually what I realized that when I was working with Ravi, it was the shortest route to getting to a point where I could start working on research problems.
Ah, I see.
So it took me like not too long to read a number of papers to get to a point where I could actually start proving some theorems.
Right.
And I think that was the main because like I mean I was also learning some of these other things which actually would have taken me a lot more time to have gone to that level. But I think it just I think kind of like clicked with Ravi and yeah I and that's when I started getting start picking up more of the number theoretic stuff.
Right. Right.
Yeah.
Yeah, I think that's a good point and maybe a generally good strategy to mention to people is that to keep in mind is think about yeah, what is the quickest route to get papers and established. I think probably in terms of like career wise, that's a good move. Like find something. Maybe I don't know, maybe a more nuanced opinion, but it makes sense to me, right? Sort of find that shortest route where you can start writing papers and making a contribution, establish yourself, and then from there you can branch out a bit, which it seems like is what you did, right?
Yes, I mean, I think you know, getting to a level where I had a very good ideas, like as to how the field works and what are some of the new questions that I could ask, which are somehow like a little bit independent of what people are working on in that field. I think that was the main thing. On the other hand, like the work I was doing in the Langlands program, I felt like would just take forever.
Yeah. As someone doing a PhD in the language program, I mean, I feel like I'm at a point where I'm starting to. It's like, oh, okay, I've got some ideas for papers. I can actually cobble things together right now. But it's well, we talked about the other day, one of my like extra passions is graph theory, and sometimes when I'm poring over these papers trying to figure out what's going on, I'm like, why didn't I just do the thing where I can like draw a picture and then it somehow seems
Well, I mean, it did take me like I mean, I did have to like assimilate a lot of Galois cohomology and deformation theory and stuff like this. It wasn't like I just
yeah
but
yeah
yeah, I think I found it like the easier of the the options in terms of like the amount of time it took to get to a stage where I could actually start working on problems. So
right
yeah, so for me, I think it is. I mean, I think it's different for different people, but for me, like working on actual questions which are sort of very concrete and interesting, uh, as opposed to spending a lot of time going through the literature and like working on something which is already very well established. I kind of like to sort of ask questions which are a little bit tangential to what everyone else is working on. So yeah, so I think for that, I mean, personally, that's kind of like what I went for at the time.
right
Yeah, so but eventually I got interested in Iwasawa theory, which is another branch of number theory. And that was because I went to the Arizona Winter School.
Oh, okay.
Yeah, and I worked with John Coates for a while at the time, and I think after that I actually um, networked with a bunch of people who did Iwasawa theory, and that's how I ended up writing my first paper in Iwasawa theory when I was a grad student. So
So I should maybe be careful because I'm looking forward to going to the next Arizona Winter School. So maybe I shouldn't tell too many people about this, but I also, as someone interested in math outreach, feel compelled to pause to give a brief advertisement, perhaps, for the Arizona Winter School. I've gone a couple times. You went at least once, or
I went around 4 times.
Okay, yeah, nice. Yeah, it's so for those of you watching, if you're, I think grad students and postdocs also attend postdocs as well.
Yes,
I think, yeah,
postdocs as well.
yeah. Arizona Winter School really is fantastic, especially if you live in a cold place. It's a nice excuse to get away somewhere warm. But they've got just absolutely fantastic world class mathematicians coming giving talks. There's normally research projects involved as well during that. So I'm guessing that that work came out of one of those projects.
Yes.
Which I've been the last couple of years I went, I felt a little too intimidated to join, but next year's topic, I'm feeling confident that I could actually make a contribution. So I'm pretty excited to, to have grown up and be at that stage where maybe I can jump in and I know I've known lots of people I've met through there that have taken part in those research projects, and those little projects that are just get started during that week have often result in papers. So it's really fantastic conference if you don't know about it. If I remember, I'll put a link in the description. If I don't remember and you're watching this, please comment and bug me and be like, "Where's the link?" Yeah.
Yeah, so I mean, I think for my project, I wasn't very successful in sort of like proving the theorem that Coates had in mind. I want to like mention that, but because it had to do with some, it had to do with a very old question, which was very hard, and the literature on this question seems to be incorrect and had to do with trying to correct some of the literature. But yeah, I think I wasn't very successful in doing that project, but at least it had me network with Professor Sujata, who was at UBC, and that's when I actually started working with her on some of the other Iwasawa theory stuff that she does. Yeah, so I would say it was not a complete failure, but it was definitely a really good experience. So
right. Well, and I think that highlights two important points for maybe some of the less experienced viewers who might be watching is first off the mathematical process. Even so maybe people are intimidated. Oh, this guy's like reading number theory in grade 9 or something. But here we find like even people who are reading number theory in grade 9, you come up against these challenges that are difficult, right? And in your working career, it's not always just sunshine and rainbows, right? You come across these problems that are difficult and you don't always obtain the results you want. And then the second thing is also, I'm ranting all the time on this trying about networking and how that's such an important thing, right? So even if some project, I don't know, trails off or whatever, you make some new connection and then that's how you get into new fields or new collaborators.
And that's something that has really surprised me. Like when I was in the beginning, when I thought number theory and in general, like mathematics was all about was you go and you solve some like open problem and you become famous and
right.
But usually what happens is you don't really like I mean of course it works out for some people, but for most of us what seems to be sort of important in the long run is the networking aspect of it as well.
Right.
So yes.
Yeah. sad news for all the loners and reclusive people who were hoping to just sit in an attic for 7 years like Wiles. Yeah. Okay, so then you right, so you met this collaborator at UBC, and so at this point you were largely working on Iwasawa theory.
I think it was a combination of both things. I was working on some of the stuff that I with my advisor at Cornell,
Mm,
and I was also branching off into Iwasawa at that time. So those were the two
Mm.
main things that I was working on at the time. So this was around when I was a third year grad student,
right.
second year, third year.
Okay, and then well, let's talk. I know something. I don't know how many grad students we have watching this channel, but something that's going to be relevant to me pretty soon is the PhD to postdoc transition. So I don't know if you want to go into detail a bit about that. Some of your experience trying to find jobs. How your maybe mindset focus or change, like some of the things you were working on in that time. How did that jump go for you?
So for me, like I so the thing is that when I was a grad student, like at least in the first few years, I was kind of like struggling to get my mathematical understanding to a point where okay, I could actually prove some interesting terms in my small area
Mm,
of interest. But I think like towards the end of my grad school, and then especially at the beginning of my postdoc years, that's when I sort of got interested in a lot of other things, like
mm,
within number theory, of course,
right.
uh, and then I could sort of like pick and choose like where I felt were the best opportunities in terms of like research.
Mm,
And that was a time. I think it was an exciting time for me because I think during my PhD I was kind of like working on this one specific area, and then okay, like if I could not like make a big splash on like this small set of problems, okay, I mean, yeah, I mean, what would I do in that situation? But I think sort of getting a little bit more breadth at the time gave me like more options to pick and choose what I actually wanted to work on
right.
and yeah, so I think towards the beginning of my postdoc was a time when things were looking good in terms of my overall mathematical growth.
And at that
Um,
time, like, were you, because sometimes, at least the way I've understood it, haven't done any postdocs yet myself, but sometimes you go and you work under someone during your postdoc, and you really work under them, right? Like you really take on their sort of project, and you sort of, maybe you write some other of your own things on the side, but so were you really under the influence and working closely under people, or were you working more on your own projects?
yeah,
Bit of both.
the combination of both.
Uh,
Yeah, so I wanted to make the most of my supervisor's expertise,
right.
and also like she had a number of other, I mean, she had some other postdocs, and I wanted to make the most of their expertise and just learn as much as I could about what they were doing and collaborate with them as much as possible and spend as much time like working with them as possible. But I also wanted to spend a lot of time doing my own stuff
Right.
and develop my own interests because I somehow like at this time I was like way more mathematically mature than what I was like as a grad student.
Right. Right.
So this was around the time when okay, like as a grad student you have a bunch of ideas and then okay, like you just write them up.
Mm,
That's uh, and then eventually you try and publish something which is significant enough.
mm,
At this time, I was like had a lot of different ideas about a lot of different things.
mm,
So it's like just pick and choose. Okay, like these ideas are not really going to lead to that good a paper, so I can just completely torpedo them and yeah,
mm,
I'm not going to pursue them. But then,
right.
so I can sort of like have more flexibility with the projects that I want to do as opposed to the ones I don't want to. So
Right.
it was an exciting time for me. The transition from PhD to postdoc. Yes.
Right. Right. And then, so how many postdocs did you do?
I did two postdocs. I did 2 years at UBC, the University of British Columbia, and then I did 1 year at the CRM, which is the Center. Okay, but it's at the University of Montreal.
Right.
It's basically affiliated with the McGill University of Montreal Concordia, if I'm not mistaken.
Right. Right.
Yeah, so it's like that was a 1 year postdoc. So I was a Simon's postdoc. It's like that's basically for someone who's already done a brief postdoc before. So that was a 1 year postdoc.
And then what was the process of ending up at the Chennai Mathematical Institute?
Yeah.
Did you have your eyes on that for a while, or was it just sort of a happy coming together of things? Like, because you said you did your undergrad there, so was there some part of you that felt like particularly drawn to it,
definitely.
or okay?
Yeah. So I applied for jobs after 1 year at UBC. So that was like in September 2021. I applied to places mostly in North America and Canada, but I also considered like the option of applying to India.
Right.
So, and this is like the one place I applied to because I was like, yeah, I know this place, I know the philosophy, it's mostly a mathematics institute, which is what I found very attractive about it. Like,
right,
it's not like a university with many different departments and just mathematics. So I think that's and it's got mathematics in its name.
Right.
Yeah. So, yeah, I sort of like that. And I've been a student there as well. So yes, I applied for a position there. I applied for positions in North America. I didn't apply to Europe. And I got an offer from there around in December, mid-December. Yeah. So and then I decided to accept that offer, and I postponed joining by a year because I also wanted to attend CRM for a year. So that was So and then it's been good. So I joined in 2023 in July.
Yeah, nice.
So yeah, good weather.
So, almost coming close to the 1 year anniversary.
Yes.
Yeah. And so, yeah, moving forward, I guess, what are some of the topics? I mean, you mentioned some interesting things you've been thinking about lately the other day, but you mentioned earlier, for example, that were considering algebraic topology at some point in your PhD, and then I think last year when you came and gave a talk, you were talking about something that was very much, knots, the relationship between knot theory and primes, and that connection to Iwasawa theory. So it seems like some of those old, things subjects you have some fondness for, you've been finding ways to sort of bring those into your research. And so, is there a trajectory that you're on now?
So the thing is that when I was an undergraduate student, I actually took a lot of interest in this field called arithmetic statistics, which is basically like in analytic number theory, we ask a lot of questions about prime numbers, and questions about distribution of prime numbers and the order of the primes according to their size. And one would like to do, it's very natural to sort of do something similar for like more objects in algebraic number theory, like number fields, for instance. So you can sort of order number fields of fixed degree and according to their discriminant, and you can sort of ask questions about the distribution of class groups, and so this sort of question it's something that has been considered for a very long time in number theory. So like the study of like class groups and other arithmetic invariants as random objects in these families is kind of like the focus of arithmetic statistics, which largely it sort of focuses on class groups and number fields and like ranks elliptic curves and so on. But my interest was, so this is something that I developed around the time when I was towards the beginning of my postdoc at UBC, was to try and merge this way of thinking with Iwasawa theory.
Mhm.
So so that's the time when I was trying to sort of look at various conjectures in Iwasawa theory, and if not prove these conjectures for all elliptic curves or for all number fields, for instance, would actually prove that they actually hold on average.
Right.
As we vary through families of elliptic curves, families of number fields.
Mm.
So it's kind of like it is motivated by the stuff that I actually used to read as an undergrad in the field of arithmetic statistics. I didn't really have the opportunity to work with someone who actually does arithmetic statistics, but that's kind of like how it came up. And so I did make some connections between the sort of the Iwasawa theory and some of these other like aspects of arithmetic statistics, and prove that various conjectures in Iwasawa theory actually hold for large families and elliptic curves and so on. So that has been an ongoing thing. And that is also related to what I talked about at the number three seminar that day, when I was considering some topological arithmetic topology analogs of these questions. So of course, like I think what I'm interested in when it comes to arithmetic topology and combinatorics in general is the sort of the analogy between number fields and knots and their Galois groups and so on, and the sort of the study of distributions of these the objects on the topological side.
Mm.
So that's kind of like where my interest is at with the graph theory and the topology.
Mm.
And this is something which is fairly new. It's kind of like people are beginning to take more of an interest in this sort of thing.
Mm.
And some of my research has to do with studying these questions in the context of Iwasawa theory, and some of them also, just purely from a combinatorial / logical point of view. So
Right.
Yes. Sorry. I mean that's a very long answer.
No, that's great. Like I said, I mean we're here to have to hear the long answers.
Right.
Yeah. I think analogies I think are one of my favorite things in mathematics, almost to the detriment where it's there's of course always the desire to go and dig deeper and prove theorems, but there's some things where I just stop and marvel at some fact, or in particular, people often talk about favorite theorems. Of course, I have plenty of theorems that I would consider my favorites, or theorems that I find really interesting. But I think what I get more excited about is actually analogies. The fact like thing in this field is secretly thing in this field. I'm enamored, and sometimes with the most simple things, or it's almost I get hung up on even going further and deeper because I'm just so I don't know, beholden by these simple things. I think you actually told me probably one of my new favorite analogies the other day, that one should think of the number of spanning trees of a graph as the class number of that graph. Actually, maybe for the audience, do you want to just give a brief explanation? It's
Okay. So
I love this idea.
Okay, so I'm not an expert in graph theory, so I just want to like make that very clear.
Sure,
It's
sure, sure.
It's on my main sort of research drive at this point, but the thing is that so like one way of defining like the class group of number field, of course, is to sort of view it as some sort of Picard group for the random integers of the number field. So we're looking at basically prime divisors, modular principal divisors.
Mhm.
And of course, like this analogy, of course, extends to like curves over finite fields, or like, and then you can talk about the Picard group in this context as well in the same vein.
Yeah. So already here we have one another analogy that I love is this fact that you go from, if you've learned some algebraic number theory, you learn about the class group in this one algebraic context, and all of a sudden you're connecting it to something you can do in like differential geometry with like Picard groups and stuff, which is already fascinating to me. But anyways, please.
Yes. In fact, there's a very interesting relationship between graphs and curves over finite fields. And this comes up in the paper that you had mentioned to me. No, day before yesterday, right?
Right.
Paper Baker and Noreen.
Right.
Oh yeah. Okay. So, but again, if I want to look at a graph, I can look at the set of divisors. These are going to be formal linear combinations, integer linear combinations of the vertices. I can look at the subgroup of divisors with degree 0.
Mm-hmm.
And then I have a notion of a principal divisor associated to a function on these vertices. So then if I look at the quotient, so I have an analogous notion of pick naught. And this pick naught turns out to be, the cardinality of pick naught turns out to be the number of spanning trees of your graph.
Yes. Amazing. So I love it. It's such, it's just like an idea. It's just an analogy, but I just love this.
So like,
so
so like circling back to what I just mentioned before. So you can take these sort of distribution questions on the number theory side and sort of ask the same sort of questions on the graph theory side, for example. Yeah. So.
Yeah. It's just, it's fun.
Yes.
So to switch gears a little bit, one thing I like to ask, normally later in the interview is your philosophical disposition of mathematics. So normally this is phrased as Platonist versus realist, or do you think about the philosophy of mathematics much and what it means? Do you care? Do you feel that mathematics is just a human invention, the word games of Wittgenstein, or is there some sort of absolute truth that you're reaching into the ether and grabbing a hold of?
Okay. Well, that's very. I'm actually not on this question. I actually would lean to the first. So I do think of it more as a human invention and it being very specific to the way in which humans think.
Right.
And whether an alien civilization would come up with the same notions in mathematics, I really doubt that to be the case. I think of it as like it has to do with it is very inherent to the human mind. Of course, it can also be very powerful, and it has a lot of applications to the real world as well. So,
right,
that's just the way I think of it.
Right. Do you think there's some? Many people say like surely some basic stuff about the counting numbers would be the same though, right? Because probably aliens have to count things, but
I am not so sure. They have need to count things. I guess, yeah, I don't know.
It could be they have very different sensory perceptions, right? Like the duck-billed platypus, I believe, can detect electromagnetic impulses in its beak or something. I remember hearing this somewhere once. So I could imagine that if some sort of alien life form had very different ways of perceiving the world. But still, one would I don't know, maybe venture to guess that
So what I believe in this context is and of course I'm sure many people will disagree with me. I think that what is at a given time what is deemed to be interesting or important in mathematics is very much subjective and is just it depends on like various political,
Mm,
I mean, it's more of a political question where, it depends on who at the time is rising to power and
mm,
has more influence in sort of deciding what questions are more important.
mm,
And, when we write our papers, we have to somehow show that, what we're doing is also sort of very much, very much connected to, what like if we can drop a lot of big names and
right,
yeah, I
right,
mean, so and sort
yeah,
of show some connections there, it's deemed to be like more important.
right.
And of course, a lot of this depends on luck. It depends on who is at what time is doing what, and what are developments in this field.
Mm,
And so like I mean, if you like do something which is considered to be very outdated, then of course people are gonna you do get referee reports that are like, okay, this stuff is interesting, but it's not the main focus of the field at this point in time,
mm,
so
mm,
yes. Uh so that I mean that definitely goes to show that I mean at least I mean of course I do agree that sometimes you see a very beautiful theorem, and I'm pretty sure that every mathematician would actually find that very beautiful and important and significant. But I also feel
mm,
like what is like what exactly is important at a given time is just it depends on the politics to a great
yeah.
extent. Yeah,
Yeah,
so
that's true. That's true. And I guess much like music or something, you sort of have this choice where if you're if you're lucky in some sense, maybe the music you like to make is very in line with what's popular, the current popular music, and then maybe you like get famous doing that
mm,
because right, but then if you really happen to like making music in a very obscure genre, you sort of have a choice of, well, do I do what my heart desires and make this very obscure music that few people will enjoy, but I'll live off this pittance and I'll be happy about it, or you make that sacrifice to do the more popular thing, which I guess you could make this analogy in mathematics
oh
too.
yeah, it's exactly the same
Yeah,
thing.
yeah,
Yeah, I mean it's much less objective than
right,
what people believe it to be the case.
right.
So um, okay, I don't want to take away from all the great achievements, but
No, that's true, but and I think it's maybe important as mathematicians that we remember there's lots of different ways in which socio political facts have an impact on the mathematics world, and lots of reasons why we should care. But yeah, one of them I think is exactly the sort of trends in mathematics when we're thinking about objectiveness of mathematics and whatnot, and I think it's important to keep in mind these sociological
yeah. So
factors.
like for instance, in my research, like things that there, it's like I have like split personalities when it comes to like
Mm,
what exactly I want to do with a certain with some of my interests, in the sense that I do want to conform
mm,
to like what the main people in the field consider to be interesting,
mm,
but I also want to be divergent.
mm,
And it's kind of like you need to sort of come up with a balance of these two things. At least for me, I'm not the kind of person who will like conform and do exactly what everyone else is doing or the main focus is. Like for me, I need to be a little bit divergent in my methods.
right.
But I felt like in some situations being a little bit too divergent, when I'm number one, it can be a little bit difficult to sort of like build things up from scratch without using other people's ideas at all.
Right.
But on the other
Right.
hand, like also like uh yes, it can be difficult to convince people that something is interesting. So I think
Mm,
it's for me it's a balance. I need to sort of have both of those things working for me, the conformist and the divergent perspectives
right.
when I'm trying to prove a new theorem.
Right. Yeah. Well, that's probably a good thing to keep in mind, is to have that balance of
Yeah, I
perspectives.
don't know why I said made a lot of sense,
Yeah.
but okay.
Ah, made sense to me.
Okay.
Made sense to me. Yeah. Yeah. Well, with that, I don't know. Do you have any parting thoughts? Maybe parting words of wisdom for our viewers at home who are in various stages of their mathematical careers.
Okay. So I think I think it is. Yes. So I think. Like I mean, for me at least, like I found it very helpful to be, sort of like learning about a lot of things outside of my immediate area of research.
Mm.
So it's like I kind of spend like 50 to 60% of my time like learning about you know things that are interesting to me in but I'm sort of like a little bit away from my immediate area of research at a given time.
Mm.
And I found that doing that is really helpful for me. Because the reason why it was helpful for me is because um, I found that, spending too much time focused on like one small area and, you know, um, was a little bit counterproductive, but sometimes just having like a lot more breadth and then picking and choosing what what research I wanted to do and where I could actually come up with the original ideas and original directions
Mm.
was and then going forward with it.
Mm.
I found that was just a lot better for me. But I'm sure that could be different for different people.
Yeah, yeah. Well, that's good to know, and almost reassuring because sometimes I feel that maybe I'm too distracted sometimes. You know, there's a breadth of things that I'm interested in, and
Right.
I'll see an interesting post on Reddit or some Discord or someone's talking about a very different field of mathematics, and then all of a sudden I'm absorbed by this thought, and then like a couple of hours.
So what I said applies to someone has gotten their PhD.
Right, right.
Like post PhD advice.
Yeah, yeah. Okay, good
Not
disclaimer.
the advice to give to an undergrad or
Uh-huh.
beginning
Uh-huh.
PhD student.
Yeah, yeah, yeah. As someone who's working on that, yeah. The advice the pre PhD advice is stay focused.
Yeah.
Yeah.
Yeah. Okay, so stay focused.
Stay focused. Unless you have your PhD, then yeah. Okay, well, thank you very much for joining me and chatting with me.
Yeah, it was really nice.
Yeah, yeah. Thanks. All right, and thanks for watching, everyone. We'll see you in the next episode.